successful landings of rovers on Mars are one of humanity's greatest achievements and one of the most spectacular things we have the opportunity to witness. But have you ever wondered how they are controlled and driven from here on Earth, more than 225 million kilometers away, with a delay of more than 12 minutes? The challenges are enormous, and to make things worse, this meticulous process of controlling and guiding the rover does not tolerate mistakes. For example, an error in choosing the best path for Perseverance could end up making it crash into a rock or placing it on a steep and dangerous slope with the risk of overturning. Another case, when the rover must approach a cliff to make observations, a calculation error could end up making it fall instead of just approaching to observe. Perhaps the most common error is in choosing the path that seems less dangerous. If that path is not analyzed correctly, it may lead the wheels to sink into a sandy area of Mars, making it impossible to get out. That is exactly what happened in 2009 with Spirit. While moving the vehicle for another walk during Sol 1899, one of the wheels ended up stuck in sandy terrain. The team desperately tried to free the rover, but without success. To make things worse, one of the wheels stopped working, leaving Spirit with only 4 operational wheels out of the 6 it had. After several months of failed attempts, the mission was redefined as a stationary platform. In other words, a single mistake can cost 10 years of work and billions of dollars invested, resulting in a rover that is either completely lost or with limited functionality. One of the key elements that makes this whole communication process possible is the Deep Space Network, a set of 3 facilities with antennas spread across strategic locations on Earth, one in the United States, another in Madrid, Spain, and the last one in Canberra, Australia. These facilities were positioned in such a way as to create almost total coverage of the planet, ensuring that, no matter the relative position between Earth and Mars, it is always possible to send or receive signals. Each facility has several antennas, some with 34 meters in diameter and one gigantic one with 70 meters. This enormous surface allows capturing extremely weak signals coming from Mars. Another fundamental element for communication is the satellites that orbit Mars, such as the Mars Reconnaissance Orbiter and the Mars Odyssey. With all this apparatus set up, once the rover lands on Martian soil, it becomes possible to start controlling it. For the signal sent from Earth to reach the rover, requesting, for example, take pictures, record a video, move forward 15 meters, or make a 90-degree right turn, it needs to have antennas to receive and transmit signals. In the case of Perseverance and Curiosity, there are 3 main antennas. The first, and most used, is the UHF antenna, or ultra-high frequency antenna, which operates in the 400 MHz range. Due to its limitations, the data transmitted by this antenna is first sent to the satellites orbiting Mars, and from them retransmitted to Earth using much more powerful antennas. There is only one problem. For the data to reach the satellites, the rover must be in line of sight with them, and that happens only a few times per Martian day. The transmission window lasts about 8 minutes. During this period, between 100 and 250 megabits of data can be transmitted. The second antenna is the X-band high-gain antenna. It transmits and receives signals directly from Earth without needing to go through the satellites. This antenna is movable, which allows it to be pointed to always maintain line of sight with Earth, which is in constant motion relative to Mars. It operates in the 7 to 8 GHz range and allows a transmission rate that varies from 160 to 500 bits per second when connected to the 34-meter antennas of the Deep Space Network, and can reach up to 3,000 bits per second with the 70-meter antenna. The third antenna is the X-band low-gain antenna, used mainly to receive signals, although it can also transmit at low rates. Unlike the high-gain one, it is omnidirectional, meaning it does not need to be pointed, ensuring more robust communication. even if limited. The commands sent to the rovers are usually not simple, like move forward. Most of the time, they are packets containing several complex commands. After choosing the destination location and analyzing the terrain, the team sends instructions such as advance 5 meters, make a 90-degree right turn, and record a panorama. Before executing, the rover itself analyzes the terrain around and, depending on the situation, can decide whether it is safe to proceed or if it should deviate to avoid risks. This is only possible thanks to the hazard avoidance software. Controlling a vehicle worth billions of dollars, more than 200 million kilometers away, with radio signals that take about 12 minutes to arrive, requires advanced technology. NASA's team combines sophisticated software, virtual reality, high-resolution satellite images, data collected by the rover itself, and even three-dimensional glasses to recreate an extremely detailed three-dimensional environment. This environment, similar to a video game, allows engineers to drive the rover safely. The software that manages this environment is called RSVP, or Rover Sequencing and Visualization Program. It has been continuously improved over the years since the Spirit mission. There are basically 3 driving modes. The first is blind drive, the simplest but also the most dangerous, in which the rover only follows straight ahead. The problem is that seemingly small obstacles can be much more dangerous than they appear. The second mode is visual odometry, in which the rover measures wheel rotations and calculates the distance traveled. But since there can be slippage, it uses its cameras to take pictures before and after movement, comparing images to determine precisely how much it has really moved. The third is autonomous mode, in which the team chooses a destination, and the rover is responsible for getting there, using its own risk analysis systems to avoid dangerous zones. This technology was already proven in 2004, when Spirit managed to autonomously avoid a 20-centimeter rock during Seoul 106. The cameras that support the navigation software are the HazCams, located at the front and rear of the rovers. There are 6 in total, 4 in the front and 2 in the back. That is basically how the rovers are controlled from Earth, remembering that behind this entire process, there is a great deal of study, dedication, and innovation. What NASA does on Mars shows just how far human ingenuity can reach, controlling a robot more than 200 million kilometers away, even with minutes of delay. Here on Earth, another challenge pushes technology to its limits, catching a 70-meter rocket while it's still in the air with astonishing precision. Click this video to know how SpaceX manages to catch Starship in mid-air and the insane engineering behind it.